Greetings and welcome to the Chemical Equations and Reaction Types Lab for Chemistry 151, where we'll explore how to balance chemical reactions and the kind of patterns sometimes that chemists see to see what kind of products are made, what kind of reactants are needed, stuff like that. This lab is really just about how to balance them, and you've got to know the right amounts that go into a reaction and also how much is coming out of the reaction, all right? We'll also look at some of the common reaction types, and in chemistry we see some patterns for chemical reactions that are fairly common. We'll go over some of those and see how that stuff all kind of rolls. The important thing to remember, though, is that this whole section is about what's called the law of conservation of mass, which just says that all the matter that goes in has to be accounted for on the way back out. Now, because chemists are concerned about atoms, that means that all the atoms that go in have to be accounted for on the way back out. You're not going to create or destroy any atoms along the way, so we have to take account into what's happening. I call this sometimes the accounting section because we're really trying to pay attention to where atoms are coming from and going to. Now, this is an example right down there of a chemical reaction. And notice here how in the central part there is an arrow. And the arrow is basically a line between reactants on the left and products on the right. And reactants are the ingredients that you need to make a reaction happen. And the products are what you get out of your reaction, all right? And most of the time, people are interested in getting a certain type of product, but you can't get products without the reactant, so they're both really important. Now, sometimes over the arrow, you'll see things like it says heat right there, or you'll see different kind of things. Those are just little pieces you will need along the way to make this happen. We're not going to focus on that part so much, but we're more interested in the reactants and products. Notice this big 2 right here. That's called a stoichiometric factor, and that's going to be really important because, again, you've got to have atoms going in equals atoms going out, and that's going to be really important to us. So again, reactants on the left, products on the right. So in this reaction here at the bottom, the K and the water are reactants, and the H2 and the KOH are the products. And we know that because the arrow designates the two of them together. In this reaction, all of the chemicals have a little state next to them, state of matter. And there's 4 of them that we'll run into in this class. If you see the little S, like by potassium, that's for a solid. If you see an L, like there by water, that's for a liquid, obviously. Sometimes it's a cursive L. Sometimes the L looks like a 1, but the hip chemist will know that it's supposed to be an L. By the H2, there's a G, which is, of course, gas. And we'll also see a lot of AQ, which means aqueous. That means that that thing is dissolved in water. So in that case, KOH is potassium hydroxide. You would have an aqueous solution of potassium hydroxide. Potassium hydroxide dissolved in water. So if you see the states of matter, great. Not all reactions have states of matter, and that's okay too. And for where you are in chemistry, I don't think you'll be expected to know any of the states of matter, but if you'd like to try or put them in, that's awesome too. It's your call. Stoichiometric coefficients are super important, and those are just the big numbers in front of the chemicals. So you can see in front of the K and in front of the water and in front of the KOH, there's a big 2. And those stoichiometric coefficients refer to that entire chemical. So that means 2 potassiums, 2 Ks. It means 2 waters. It also means 2 potassium hydroxides, KOH, and the 2 refers to everything that's past it. So 2 waters would be 2 times 2, 4 hydrogens, and 2 times 1, 2 oxygens. And for KOH, that would be 2 Ks, 2 Os, and 2 Hs, all right? They're really important. At this level, when you're balancing chemical equations, you don't want to change the internal numbers. Like you wouldn't want to turn water into H3O or something strange like that. Don't change those numbers, but you can definitely play with those numbers, the stoichiometric coefficients. And you always want to make them as small as possible. Small whole numbers are what chemists are always after. So let's balance a chemical reaction, all right? First of all, you got to start with the correct formulas, and this is where where the nomenclature comes in so handy. So here's an example. Sulfuric acid reacts with sodium hydroxide to create sodium sulfate and water. So in the nomenclature lab, we saw how sulfuric acid is the most common version of sulfur with oxygen, that's H2SO4. Sodium hydroxide is a metal with a hydroxide polyatomic, a base. Sodium sulfate is on the product side. That's Na2SO4. Sulfate is -2 and sodium is +1. So you need two positive ones to balance the sulfate. Plus water, H2O. This is the unbalanced chemical reaction, and we'll balance it in the next step. But the important thing here is that once you have these names down, you don't want to turn H2SO4 into something like H2SO5 or H2SO3. Keep those coefficients as they are. Don't change them, all right? We'll change the big numbers, the stoichiometric coefficients, but we won't change the internal numbers, and that's important. Now, the next step is you want to add appropriate coefficients to balance those numbers of atoms of each element. So you were probably seeing, or maybe you did, maybe you didn't, no problem. But for example, sodium, there was an Na2SO4, two sodiums, but NaOH only has, of course, one sodium. So we're going to add a 2 in front of that NaOH, and that will make those two parts go together, which is really cool. So sodium now is balanced on both sides. Again, we're not going to make it Na2OH or something like that. That would break the charges, but you can add a big 2 in front of the Na, which is a pretty cool thing. Also, notice here that there's one sulfate on the left, an SO4, and one sulfate on the right. If you have a polyatomic ion on both sides, I would recommend keeping it together. Like, don't break it up into one sulfur and 4 oxygens. You can see the oxygen is part of the NaOH and the water as well. You just want to keep the sulfate all together, all right? Don't break it up into individual pieces, and that makes your life a lot easier. Okay, if you look at this long enough, then you've got a lot, the sulfates are good and the sodiums are good, but there's still some problems. So for example, you can see you've got H2 on the H2SO4, and you've got OH on the NaOH. And the product side, the right side, you only have H2O. So the next thing to do is just make sure everything is balanced out, and we've got to play with that water, all right? So because we had too many hydrogens and too many oxygens on the reactant side, and you can see there's H2SO4, and this 2 right there means 2 oxygens and 2 hydrogens. So we've got a total of 4 hydrogens and 2 oxygens on the reactant side. Water is just 2 hydrogens and 1 oxygen, but we can rectify that by putting that 2 right there. That makes 4 hydrogens and 2 oxygens on both sides, and we're good to go. So this reaction right here is the balanced reaction, and that's totally cool. Now, there is a step 4, and it's not a big deal here, but you want to make sure that you're using the smallest whole numbers. So for example, the reaction we just wrote, we could have also had a balanced reaction by having double the amounts. So 2 H2SO4 plus 4 NaOH makes 2 Na2SO4 plus 4 waters. And those atoms would have all been balanced, and they would have been fine, but it's sloppy. In chemistry, we try and use the smallest whole number ratios, smallest whole number coefficients. So step 4 is just asking you to check that out. Most of the time it's not a problem, but you do want to check it out just in the offhand. You do have some kind of numbers that are too big. So make them the smallest whole number ratios possible. Let's look at some examples. This is an example where I would ask you to balance calcium plus nitrogen, making calcium nitride. So we'd have to figure out, of course, the names of the chemicals first. I am putting up a reminder. In this section, it's really important to remember the 7 diatomics. Have no fear of ice clear brew or Hunkel Briff, which is what I wrote right there. Those are the 7 that exist in pairs of atoms. Calcium is not one of those. Calcium is not Hunkelbrief or have no fear of ice clear brew, but nitrogen is. Nitrogen is the N of Hunkel, or have no fear. It's the no part. So you can see what we're doing here. Calcium, not a diatomic, listed by itself. But those 7, which do pop in a lot, you want to write them in pairs. So we'd write calcium plus N2, because N2 is a diatomic. Calcium nitride is going to have a calcium plus 2. It's a fixed charge metal in group 2A, so positive 2. Nitride is nitrogen, a non-metal in group 5A, 5 minus 8. Nitrogen is going to be negative 3. So when you make a balanced chemical formula for calcium nitride, 3 times 2 is 6, common denominator, so 6 divided by 2, 3 calciums, 6 divided by 3, 2 nitrogens, calcium nitride, Ca3N2. So calcium by itself plus N2, the diatomic, makes Ca3N2, and now we can balance it out. The N's are already balanced. Calcium needs a different stoichiometry in front of it. 3Ca plus N2 makes Ca3N2 would be the balanced reaction. Here's another example. Magnesium chloride plus sodium phosphate makes magnesium phosphate plus sodium chloride. So again, we've got to figure out charges on all these things, make sure they balance. Magnesium is positive 2, chloride is negative 1, sodium is positive 1, phosphate negative 3. So when you put all these together, magnesium chloride, positive 2 with negative 1, would be MgCl2. Phosphate negative 3 with sodium plus 1 would be Na3PO4. Sodium chloride, NaCl, and magnesium positive 2 with phosphate negative 3. When you do it, Mg3 parentheses PO4 parentheses 2. And again, notice when there's more than one polyatomic, make sure you put those in parentheses. Don't use parentheses for anything else. For example, sodium phosphate didn't have parentheses, but when you've got more than one, use the parentheses. So this is the unbalanced reaction, and you can see there's some issues. So for example, magnesium phosphate has 2 phosphates, sodium phosphate has just 1. So leave the phosphate as a unit and start balancing it. And you don't have to follow it the way that I'm doing it if you have your own way, which is fine too. But what I would do probably on this one is I would start by putting a 2 in front of the sodium phosphate, and that makes 2 phosphates on the reactant side, and then 2 phosphates on the product side. But you can see we've got like 3 magnesiums and chlorines coming in 2s, and there's 6 nitrogens, etc., etc. So you got to play here a little bit. So let's say that we do that. We say, okay, 3 magnesiums, 3 MgCl2s, but now I've got 3 times 2, 6 Cls. I've got to put a 6 right there. Is everything balanced? And sometimes these can get a little crazy. So this little part right here is a way that you can always check yourself. If you have a reaction which you think is balanced, this one right here, check yourself. Make sure that the atoms or polyatomic ions on each side are the same. So you can see here what I've done is I kind of drew like a line. And on the reactant side, the left side, 3 times 2 would be 6 Cls, and 3 times 1 would be 3 Mgs, and 2 times 3, 6 NAs, and 2 phosphates. Now if this is balanced, the product side will be the same. So on the product, the right side, 6 NAs, 6 times 1, 6 Cls, 3 Mgs, and 2 phosphates, and you can see that those numbers are the same on both sides. Balanced reaction. Happy chemist. All right. This is like everything that's going in, taking into account on the way back out. Life is good. It's a trick. Sometimes you'll want to use it. Sometimes after a while you'll get so bored it takes forever, so you won't want to use it. But when you're learning, I do recommend just checking yourself to make sure that it's balanced when all is said and done. When you look at all chemical reactions, there are 6 categories, 6 reaction types, which are very common when it comes to chemistry. And you can see them listed right here: combination, decomposition, single replacement, combustion, acid base, and precipitation reactions. And if you can get these 6 reaction types down, it makes your life easier, because a lot of times you'll be able to predict the products without actually doing the reactions, and that's really, really handy. Now, there's a lot more than just these 6 types, all right? There's more than this, but these are a really nice overview as to the different things that are possible. So we're going to go through these. Several of them we'll do in the actual lab. The other ones we'll talk about here real fast and see what's all happening. So the first is called a combination reaction. And you're literally taking 2 or more chemicals and just combining them into one. So imagine we have chemical A and chemical B, and on the product side, we would literally have them mixed together. So you can see here some examples. The first one is magnesium plus oxygen, making magnesium oxide. Now, on the product side, we've got to take into account the charges of the different species. So for example, for the first one, magnesium's +2 and oxygen's -2. So they come together in 1-to-1. But oxygen, a diatomic, have no fear, ice clear brew, it's one of the 7. So we've got to write it as O2. So because of the diatomic, hence why they're so important, we have to have 2 MgO, and then we can have 2 Mg to cancel it out. And again, if you're ever uncertain, you can double check that the atoms on both sides are balanced, but you should be good to go. The second one, same kind of thing. Chlorine is one of the diatomics. When Na and Cl come together, it's not NaCl2. Na is +1, group 1a. Chlorine, group 7, 7 minus 8, -1. NaCl. So we'll need 2 NaCls. That'll balance the Cl parts out on reactant and product side. We'll have a 2 right there to make the sodiums balance. And the last one, which is actually the way they make sulfuric acid, takes sulfur trioxide plus water. And when you combine those together, you make sulfuric acid, H2SO4. That's just simple. Everything is balanced. You can check it out. Okay, what I'm going to do now is show you a quick video of some combination reactions that I would have done as a demo if we would have had this class live. Check it out, and I'll talk about the other types here in just a little bit. The second kind of reaction we're going to look at in this lab is called a decomposition reaction. And it's basically when you have one chemical that's breaking down to 2 or more chemicals. Sometimes you can have a whole bunch of them. It depends on what it is. And there's lots of examples of this. Here's one, mercury oxide, mercury 2 oxide, breaks down into pure mercury and oxygen. And again, remember, have no fear of ice clear brew. Oxygen is a diatomic, O2. So because of that, we put a stoichiometry of 2 and 2 mercury. The second reaction is one we'll do in lab later. It's a potassium chlorate, KClO3. Potassium chlorate breaks down into potassium chloride and oxygen. Now again, oxygen is a diatomic, so it comes out in 2s. Potassium chlorate has 3. So we have to use a common denominator of 3 and 2, 6. 6 divided by 3 oxygens in potassium chlorate. 2 goes in front of the KClO3. 6 divided by 2 in the diatomic oxygen. We're going to put a 3 right there. And when you balance it out, you're going to get 2 KCl's. So all these decompositions, one big thing is breaking down into 2 or more things. And at this point, let's look at a video of what we would have been looking at in lab if we would have had this lab in an actual lab room environment. You can get a sense for the kind of energy and processes involved in decomposition reactions. The third kind of reaction is called a single replacement reaction. And single replacement reactions are kind of like dances. And in a dance, maybe A and B are dancing together, and C says, hey, I want to dance with your date A. And so C and A are kind of like trading places. So you can see that now A is dancing by itself, while C and B are dancing together. That's the idea. Single replacement. One part is replaced by another part. The only tricky thing is that you have to have metals replacing metals or non-metals displacing non-metals. So in these two examples right here, A, C, and M are all metals. So in the one we just talked about, A and C are trading places. So C starts dancing with B and A is by itself. In the second example, X and Y are non-metals and they're pushing each other out. So M starts dancing with X while Y is by itself. So when it comes to single replacement, just make sure the same type is being exchanged with a similar type. And here's some examples of how this works out. In this first example, zinc and silver are both metals. And so what's happening here, zinc and silver are trading places. So silver is by itself, and then zinc starts dancing, if you will, with nitrate. Now, silver and zinc are both part of the stairs. Zinc is almost always positive 2, and silver is almost always positive 1. So when zinc starts dancing with nitrate, it's going to be positive 2. You're going to need 2 negative 1 nitrates for every positive 2 zinc. Silver, which is usually positive 1, needed only 1 negative 1 nitrate to dance. So you can see why we need to have 2 in front of the AgNO3 to make the nitrates okay with zinc, and that means that 2 silvers are going to be replaced. In the next example, it's not the metals that are exchanging, it's the non-metals. Chlorine and bromine are both on the right-hand side of the periodic table. They're both non-metals. So in this example, chlorine and bromine will trade places. So at the end, sodium starts dancing, if you will, with chlorine, and bromine is left by itself. Now, both chlorine and bromine are some of the diatomics. Have no fear of ice clear brew. So you list them both as diatomics, Cl2, Br2, balance them out, and you're good to go. Let's look at some examples from lab as to what we would have done. This next type of reaction that's very common is called a combustion reaction. And we're not going to look at this type of reaction in lab, but we will look in the problem sets and in the materials a little bit as to what's happening. Combustion is really important when it comes to organic chemistry for identifying compounds, so it is very common. In a combustion reaction, you start with something organic, which is usually carbon and hydrogen. Sometimes there's some oxygen, whatever. You burn it in oxygen, pure O2, and the only products in a combustion reaction, carbon dioxide and water. So all combustion reactions, something organic, something with carbon, hydrogen, maybe oxygen, that burns in O2, those are the reactants, something organic and oxygen, and the only products, carbon dioxide and water. So here are some examples of different combustion reactions. The first one, C2H4, is something organic. It's burning in oxygen. You can see that water and CO2 are the products. In the second one, C6H12 is the reactant. It's burning in oxygen, making CO2 and water. And this last one, we have a carbon, hydrogen, and oxygen containing species. And those are actually pretty common, but same idea. That burns in O2, makes CO2 and water. We'll talk more about these in the problem sets and in lecture, but it is kind of cool to know about them and what they're all about. They're very common in chemistry, so that's why I'm introducing it here, even though our lab won't have a lot to do with it. The last two types, which are called acid-base reactions and precipitation reactions, both fall under a common category, which is what's called a double displacement reaction. And in a double displacement reaction, it's also kind of like a dance, like we talked about earlier, but in this case, the dancers are trading partners, okay? So if A and X are dancing together and B and Y are dancing, and let's say that A and B are metals and X and Y are nonmetals, then in this double displacement, A starts dancing with Y, and B, who is now partnerless, starts dancing with X. And both acid and base and precipitation reactions follow this pattern. In the acid-base reaction, an acid has H listed first with some kind of X next to it. The base has a hydroxide, OH minus, with a metal, M. So in this kind of dance, M and H are like the positive parts, and the X and the OH are the nonmetal parts. So you can see on the other side, M and X are now dancing together, and you also have H and OH dancing, which is water. So in an acid-base reaction, the acid, hydrogen listed first, and the metal hydroxide base create water all the time, H2O, which can be listed H2O or HOH if that's easier. The other piece, which here is MX, is called a salt. And a salt is a chemical term that's used to describe the product of an acid-base reaction. You can just call it whatever, but that's what the fancy name is. All acid-base reactions, acid plus base makes water plus some kind of a salt. Now, in a precipitation reaction, it's similar, all right? You've got A metal and B metal, and they're currently dancing separately with X nonmetal and Y nonmetal. And you can see here, once again, A and B are trading places. So you end up with AY and BX. But the difference in a precipitation reaction is that one of the products, maybe both, but more likely one of them is a precipitate. And a precipitate in chemistry is just a fancy name for a solid. So making a solid, making a precipitate, is what distinguishes precipitation reactions from acid-base. Acid-base, you make water and a salt. In precipitation, you make some kind of a solid. Here's some examples of acid-base reactions and precipitation reactions and how they work out. Now, the first example here of an acid-base reaction, that's nitric acid, HNO3, reacting with sodium hydroxide, again to make water and what chemists call a salt, which is just the other product of a acid-base reaction. So again, the Na and the H are both positive. They're trading places. So H starts dancing with OH, which is water, and the the Na and the NO3 come together to make sodium nitrate. The second example, hydrochloric acid, HCl plus NaOH, and again the H plus and the Na plus, those are both positive metal-like things. They'll trade places with each other. You end up making again HOH, H2O, water, and in addition the salt here, sodium chloride. Sodium chloride is table salt. It's also a chemical salt here because it's the product of the acid-base reaction too. Woohoo! Anyway, the next two examples there are precipitation reactions, and again, same idea. The metals trading places with each other, so silver and sodium trading places to make AgCl and NaNO3. And there are ways to predict it, but silver chloride is a precipitate. It's a solid, and that's something that we'll look at in a future chemistry course or in Chemistry 221. But the idea is the same. They're exchanging the double displacement dance, and one of the products is going to be a solid. And the last one there has lead 2 nitrate, Pb, or lead nitrate, PbNO32. It's reacting with Ki, which is potassium iodide, and lead 2 iodide, PbI2, is a solid. It's an insoluble compound, a precipitate. And the other product then would be potassium nitrate, the leftovers and stuff that are happening. And again, the goal in a precipitation reaction is that you don't know maybe which one is going to be a solid at this point, but you can at least see it's a precipitation based on the products. At this point, let's look at a lab video that shows some examples of how precipitation reactions and acid-base reactions can be. Okay, at this point, I think you're ready to tackle the balancing of equations lab. I think you'll have no problems with it. If you do have any problems, be sure and get a hold of me. I'm more than happy to help. Make sure you watch out for those crazy diatomics. Have no fear of Ice Clear Brew or Hunkelbrief. They will pop up a lot in this lab, but you'll be good to go and set them up. And again, if you do have any questions, be sure and let me know. Good luck with your lab.